In this example, we look at data from a two-way table. The following data was collected from students in a statistics class in Los Angeles. This is a two-way table because we are comparing two different categorical variables. On the horizontal part of the table, we have eye color. You can see our choices are blue, green, brown, and dark brown, and those values correspond with the different columns. At the bottom of each column, we have the total of the eye colors for each of those color choices. Our second categorical variable we're studying is hair color. So over here on the vertical part of the table, corresponding with the rows, we have the different hair color choices. So the hair color choices for this class were blonde, red, brown, and black. Our total for these hair colors are over in the furthest column over, so we've got totals corresponding with each hair color. So our first question is asking us how many students in the class have brown hair and green eyes. So we come here in the table to find the brown hair row and come over to the eye color that corresponds with green in the column, and you can see the two students there. That's not the value I've circled, it's next to the one I've circled. We'll come to the circled value a little bit later in this work. Question B asks us how many have black hair and brown eyes. So we would go down to black hair color in the bottom row and over to brown eye color in the middle and verify there are 7 students there. So now part C is asking us to start to think about the part out of the total, or what fraction. So when we start to think about the part out of the total, whether we're reporting as a fraction or decimal, we are calculating a probability. So when we're asked what fraction of the students have brown hair, we can look at the brown hair row and go to the total for that row. So that's the 10, where I've got the green arrow drawn up here. So there are 10 students in class who have brown hair out of 36 total students in class. We see in the bottom right corner the total there is 36, whether we add up the rows or the columns. Either way, we get the same value. We can reduce 10 out of 36 down to 5 out of 18. I still like to think about things as a decimal because then I can think about it out of, 1.0 total, or move it to a percent and think about it as a percent out of 100%. So when I did 5 divided by 18 and rounded to 4 decimal places, I got this 0.2778 after rounding. So you could say about 27.78% or about 28% of students in this class in Los Angeles have brown hair. This is a marginal probability, and we get that name because our value 10 from the total brown hair came out of the margin, out of the right-hand column where we have all the hair color totals. So the right-hand column has all the totals for every hair color choice, and similarly related, the bottom row has all the totals for each of the eye color choices. Imagine if we were making a bar plot of hair color. The blonde hair bar would be 6 tall, the red hair bar would be 7 tall, the brown hair bar would be 10 tall, and the black hair bar would be 13 tall. So we can imagine these totals over in the right-hand column as corresponding to the heights of a bar plot. So we can think about it as a marginal probability distribution if we were just doing a graph of hair colors. Similarly, if we were just doing a graph of eye colors, we would use the values in the bottom row. So question D takes us to thinking about what fraction of students in the class have brown eyes. So we come up to the brown eye color column in the middle, and we see the total down there is 17. So we can say 17 out of 36. Because that value 17 came out of the margin, we are again going to think about this calculation as a marginal probability. So marginal probabilities are any calculations where we're counting the whole group out of the total. And in a two-way table, the counts for the whole group come out of the margins, whether it's the bottom row like for eye color here or the right column like for hair color here. All right, and then our 17 out of 36, I have to convert that to a decimal to be able to think about it more comparably. So that is 0.4722 as a decimal, or you could think about it as about 47% of students in this class in Los Angeles have brown eyes. So we've already talked about question E, what do the values in the bottom row represent, excluding the bottom corner. So these bottom row values, 6, 9, 17, and 4, are the eye color totals. So I said these are the eye color totals for each category. Question F asks about the values in the right-hand column. So that's our 6, 7, 10, and 13. Those are the hair color totals. And then there's a note down here. So by the way, for any two-way table representing two categorical variables, the totals in the bottom row and right-hand column, excluding the corner, which is our total of everybody in this class, are known as the marginal distributions. I like to think about them, as I said, if I was making a bar plot of these categorical data, this is how tall the bars for each category choice would be. Question G asks us to think about what does that value in the bottom right corner represent and how do we get this number? So we know that's 36 total students in this class. So if we do the hair color total, adding up the hair color values in the right-hand column, we can add 6 plus 7 plus 10 plus 13, and that gives us 36 students total. We could also add up the eye color total from the values in the bottom of the table. So 6 plus 9 plus 17 plus 4 also gives us 36 students. When I construct a table, I like to double check both calculations to make sure I haven't made any typos or mistakes counting. If your rows and your columns all add up to the same total value, you know you've done your table correctly. Question H asks us about what fraction of students in the class have brown hair and brown eyes. So this is where in our table brown hair and brown eyes overlap. So this is that 5 that I've circled here. So we come to the brown hair color row and the brown eye color row and we find the overlap. So this value 5 that we're measuring in our probability comes from inside the table, and it corresponds with 2 overlapping categories. This student both has brown hair and brown eyes if they're in this count of 5 students. So we say this is a joint probability. So notice when I do my probability notation, in the parentheses I said brown hair and brown eyes to indicate both of those have to be true. And so these are 5 out of the total 36 students. The difference between finding a joint probability and a marginal probability is our number for the joint probability numerator comes out of the inside of the table because it's where 2 categories overlap. I want to convert the 5 out of 36 to a decimal so I can think about it in terms of relative to the whole values. So 5 out of 36 is 0.1389. So you can think about that as about 13.89% or 14% of the students in this class have brown hair and brown eyes. And I've drawn an arrow here to my probability notation to show that inside the probability notation, I'm saying brown hair and brown eyes to indicate that both categories are occurring. The students counted have both brown hair and brown eyes. Question I asks us, what fraction of red-haired students in the class have green eyes? So we are not looking at all 36 students anymore. We are just looking at the red-haired students. This is known as a conditional probability calculation because we're limiting who we're looking at. We're restricting our calculation in some way. So in this case, the condition is that we are restricted to red-haired students. So we come up to our table and we see, if we look at the second row, that's where the hair color red is. There are 7 students total. So all of our calculations here are just going to come from the red hair row. We're not using the rest of the table because we are restricted to this condition that the student has to have red hair. How many of those with red hair have green eyes? It looks like our total is 3. So just looking at the red hair row, we're going to take 3 with green eyes out of 7 total for our probability calculation. So the way we write a conditional probability is in shorthand notation, we can say P for probability, and then in parentheses, we can say green eyes because that's what we're measuring. And then we draw this line here to restrict it to students with red hair. So it helps me think about the fact that the restriction with red hair corresponds to what I'm going to put in my denominator. So since there were 7 students with red hair, the second part of our probability notation after the line, who we're restricting it to, I know I'm going to have 7 students in my denominator for this calculation. This is not out of the whole class. It's just restricted to these students with red hair. And then the numerator is going to be out of those 7 students, how many have green eyes. So we have 3 out of 7, or if we convert that to a decimal, it's 0.4286, or as a percent, we would say 42.86, or about 43% of the red-haired students have green eyes. So not the whole class, just the red-haired students. When you do conditional probability calculations, you can restrict to either a column or a row. In this case, we restricted to the red hair row, but there's no reason we couldn't have done a similar calculation restricting to a certain eye color of our choice. Question J asks us to think about the total number of students in class. So suppose the number of students with blonde hair was the same, but the total number of students in the class was actually 500. Would reporting the number of students with blonde hair still mean the same thing? In other words, would reporting the number of blondes out of 500 students mean the same thing as reporting the same number of blondes out of approximately 36 students? Why or why not? How could you make the difference evident even though the number of blondes is the same in both situations? So if we have a class of 36 students where 6 are blonde, the probability of being blonde is 6 out of 36. If we divide that as a decimal, it's 0.1667. Now, if we shift to a class of 500 students, but still only 6 are blonde, our probability that a student is blonde is 6 out of 500. If we divide, we get 0.012. So this is a big difference when we compare with a decimal. If we want to think about it as percents, that's a difference of 16.67% versus 1.2%. So about 15% difference. So when we compare with the decimal, we can see that the change in the denominator makes a big difference. So we can't just report numbers and probabilities. We have to report either fractions so that we can see the denominator or decimal form so that we can do a comparison. So when you report a probability, you always need the denominator if you're writing it as a fraction, or report your probability in decimal form.